A ChE column is an equipment commonly used for gas absorption, which is one of the prime and most common gas-liquid mass transfer operation. Contactors used from time to time and their primary process applications are listed in Table 14-4 of Perry's Chemical Engineering Handbook 8th edition. By far, the most common types of contactors used for gas-liquid mass transfer operations are tray and pack towers. As presented in the table, a tray column or tower may have a cross-flow or counter-current mode of flow. It has an integral cross mechanism and a continuous phase of liquid and/or gas. It is used primarily for distillation, absorption, stripping, direct contact heat transfer, and washing operations. A cross-flow tray, as illustrated in Figure 14-17 of Perry's Chemical Engineering Handbook 8th edition, consists of the bubbling area and the downcomer. The mechanism inside the cross-flow tray is 1. The liquid descending the downcomer from the tray above enters the bubbling area. 2. In the bubbling area, the liquid contacts the gas ascending through the perforations, forming froth, emulsion, or spray. 3. An outlet weir on the downstream side of the bubbling area helps maintain the liquid level on the tray. And 4. The froth overflowing the weir enters the outlet downcomer. In here, the gas disengages from the liquid and the liquid descends to the tray below. I have here a video which will clearly show you the mechanism inside the tray tower. The bubbling area can be fitted with numerous types of tray hardware. The most common types by far are sheave trays, fixed valve trays, and moving valve trays. Sheave trays are perforated plates. The velocity of upflowing gas keeps the liquid from weeping or from descending through the perforations. At low gas velocities, liquid weeps through the perforations, bypassing part of the tray and reducing its efficiency. Because of this, sheave trays have a relatively poor turndown. Fixed valve trays have the perforations covered by a fixed cover, which is often a section of the tray floor pushed up. As shown in the pictures, the liquid will also be prone to weeping if this kind of tray is used. Their performance is therefore similar to that of sheave trays, low tray efficiency and poor turndown. Moving valve trays have perforations covered by movable discs or valves. Each valve rises as the gas velocity increases. The upper limit of the rise is controlled by restricting legs on the bottom of the valve or by a cage structure around the valve, as shown in the picture. In contrast with sheave trays and fixed valve trays, moving valve trays give a good turndown, since as the velocity of the gas falls, some of the valves close completely, preventing weeping. To know what type of tray must be used for different conditions, Table 14-5 gives a general comparison of the common tray types assuming proper design, installation, and operation. It can be noticed that the capacity, efficiency, entrainment, and pressure drop of sheave and valve trays are comparable. The turndown of moving valve trays, about 4:1 to 5:1, and with some special designs achieving 8:1 or more, is much better than that of sheave and fixed valve trays, which only have about 2:1 or 2.5:1. Sheave trays are least expensive anyway, while valve trays cost only slightly more. However, the small additional cost is usually justified by the energy saved even during short turndown periods. When it comes to the maintenance, fouling tendency, and effects of corrosion, it is least troublesome in fixed valve and sheave trays, provided that the perforations or fixed valves are large enough, and most troublesome with moving valve trays. So what type of tray is much better to use? When fouling or corrosion is expected, or if turn down is unimportant, sheave and fixed valve trays be rare, while if high turn down is required, it is better to use moving valve trays. Now let's go on with the definitions. Some of the tray areas which will be defined are illustrated in figure 14-17. The total tower cross-section area is the inside cross-sectional area of the empty tower, without the trays or downcomers. The net area, also called free area, is the smallest area available for vapor flow in the inter-tray spacing. It is the total tower cross-sectional area minus the area at the top of the downcomer. The bubbling area, also called active area, is the area available for vapor flow just above the tray floor. It is the total tower cross-sectional area minus the sum of the downcomer top area, downcomer seal area, and any other non-perforated areas on the tray. The whole area is the total area of the perforations on the tray. It is also the smallest area available for vapor passage on a sheave tray. The slat area is normally the smallest area available for vapor flow on a valve tray. The open slat area is the slat area when all valves are open. The fractional hole area is the ratio of hole area to bubbling area for sheave trays and the ratio of slat area to the bubbling area for valve trays. For the vapor and liquid load definitions, we have F factor F, C factor C, wear load, and downcomer liquid load. F factor F is the square root of the kinetic energy of the gas. The velocity in the equation is usually based on the total tower cross-sectional area, net area, or bubbling area. C factor C, defined in the equation, is the best gas load term for comparing capacities of systems of different physical properties. It is the same units as velocity, meters per second or feet per second, and is directly related to droplet entrainment. For the C factor, as with the F factor, the user should be aware of any data for which the area basis is not clearly specified. The wear load or liquid load for trays is normally defined as the volume of liquid over the length of the outlet wear. This definition describes the flux of liquid horizontally across the tray. For downcomer design, the liquid load is usually defined as the liquid velocity at the downcomer entrance or the volume of liquid over the downcomer entrance area. Three main flow regimes exist on industrial trays: the froth, emulsion, and spray regime. These regimes may all occur on the same tray under different liquid and gas flow rates as shown in figure 14-19 of Paris Chemical Engineering Handbook, 8th edition. Froth regime or mixed regime is the most common operating regime. Each perforation bubbles vigorously, and the bubbles, of non-uniform sizes and shapes, circulate through the liquid rapidly and travel at varying velocities. The froth surface, mobile and not level, is generally covered by droplets. Bubbles are formed at the tray perforations and are swept away by the froth. As gas load increases, jetting begins to replace bubbling in some holes, and the fraction of jetting holes increases with gas velocity. When jetting becomes dominant or replaces 45 to 70% of the bubbling tray holes, the dispersion changes from froth to spray. The second type of flow regime existing on industrial trays is the emulsion regime. In industrial practice, it is the most common in high pressure and high liquid rate operation. At high liquid loads and relatively low gas loads, the high velocity liquid bends and tears off the swarms of gas bubbles leaving the orifices, so most of the gas becomes emulsified as small bubbles within the liquid. The mixture behaves as a uniform two-phase fluid obeying the Francis Ware formula. The last type, spray regime or drop regime, frequently occurs where gas velocities are high and liquid loads are low, like in vacuum and rectifying sections at low liquid loads. At these conditions, the dispersion becomes a turbulent cloud of liquid droplets of various sizes that reside at high elevations above the tray and follow free trajectories. Some droplets are enchained to the tray above, while others fall back into the liquid pools and become reatomized. In contrast to the liquid continuous froth and emulsion regimes, the phases are reversed in the spray regime. Here, the gas is the continuous phase while the liquid is the dispersed phase.